So we are looking at something called as Pascal's law, but before that, let me start off with this conversation. So we have everyone has pretty much used buses, right? They're pretty huge. They can go decently fast. But my question to you guys is, how is that a pedal? If you guys don't know about it, I mean, yeah, you guys are old enough to understand this. How is that a vehicle like this can be stopped just with a pedal? People push, that's supposed to be a leg and that's supposed to be a pedal. People push and the vehicle stops. If you guys don't know much about driving, so we have something called as brake, and of course you guys know brake, acceleration, brake and clutch and all of that. So a push of a brake, pedal per se, can get this to stop. But it's already, it's pretty huge. First thing. Second thing is it's already moving it has significant speed. So my question is again, with a small push on the brake pedal per se, right? This is supposed to be brake pedal. We can get this entire thing to stop. So how is that possible? So even at other end, we have a tiny hydraulic jack that can lift pretty heavy things. So I think you guys will not be familiar with that. Anyways, point is, the secret, it lies in this fascinating behavior of liquid. So we use it every single day, but of course we don't think about it. And one principle that I can explain all of this fascinating things is your Pascal's law. So let's look at it. So Pascal's law, there are quite a few ways that I've stated over here. So Pascal's law states that the pressure P exerted at any point on the enclosed liquid is transmitted equally in all directions. Okay. It might not make that much sense as of now. As in when you proceed through this section of the videos, then it'll make sense. Okay. So you don't have to make sense of all these statements as of now. Right. So let's look at the second statement. The pressure P in a fluid at rest is same at all points if we ignore gravity. It's not easy to imagine. Okay, guys, don't worry. A change in P applied to any closed incompressible fluid is transmitted undiminished to every point of liquid or fluid, that is, and the wall of the containing vessel. Walls of the containing vessel. So all of this we have few applications and we will see how the behavior per se. Okay. Then the statement will make more sense. And for this, fluid at rest is same at all points if we ignore gravity. So if we ignore gravity, how fluid behaves is something that I want you guys to look into. Okay, so you guys have a small homework now. So you need to pause the video and have a look at it. So you need to web search. So you need to web search the following. That's supposed to be web and this is search. Okay, so what I want you guys to do is you have to go online and look at International Space Station. ISS? No, wait. Is it ISS? Anyways. So I'm talking about International Space Station and you have to search for liquid. So basically how liquid is in the absence of gravity is what I want you guys to have a look. You can web search that also, liquid with no gravity. So search this, have a look. So you get to see weird behavior of fluids, There are quite a few recent videos that has come up which astronauts have done on the request of I think teachers or civilians, I forgot who, but yeah, people on the surface of the earth basically. So we have one particular experiment that I can think of it's pretty good actually. It went viral also. So we have a wet cloth and astronaut takes it up and he squeezes it. it, as if when you're washing clothes, we squeeze the water out. Now he does that. It's pretty good, that it's pretty good. It's actually pretty useful for explaining quite a few things that we're learning over here. So you should please search all of that. Please search. I hope you guys have done. So some of the statements might make sense now. Okay. So let me prove it the boring way, that is with math. Math is not boring, but compared to all of those, yeah, it might be. Okay, so what we're looking at is the proof follows this way. So what we're looking at is we have a container. We pick up a very small part of, this container has some liquid first thing. So in this liquid, we are picking up a very small part, a tiny part, and this is it. It's it's right angle prism in structure, and we have labeled it as well. So as shown in the figure, we're considering a small element ABC and DEF, a right angle prism in a fluid at rest. So this fluid is at rest. The element is assumed to be infinitesimally small, a very, 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 very small part or section of this fluid, such that all its points are at the same depth. Of course, technically it's not, but for us, the difference is not a big thing. So allowing us to treat the effect of gravity as identical for the entire element. So we need to consider this very small section to discuss this. Okay. So again, very simple thing. Don't get confused with the statements and all of this. It's a fancy way of telling that we're considering a very small section of water or any fluid that is at rest. That's it. Nothing else. Okay. So now we know that the pressure, the force exerted on this section of the water or fluid will be, the surface will experience perpendicular forces. It would be something like this, right guys? All these are perpendicular forces. So I can give it some name. This I can call it as FB. This surface is B. This can be A, B, and C. So this is the entire force that is acting over this surface. FA is the entire set of force that is acting on BC, FE, and FC is a force that is acting entirely on AD, EB. Okay. Now, taking up a free body diagram. So that is your horizontal and vertical line. Oh, I got it right. Okay, along the horizontal we have, go that well, yeah. So this is FC and this is FA and this is FB. Okay, FB is something like this. Now I need to resolve this force, so I need an angle. I'll take this as the angle. And now in this figure, we need to figure out where that angle is. So we have, let me actually again go to the axis X and Y and all of those. So what we are looking at is, say, this surface BC, this line BC. Okay, yes. And that's your AC. And to AC, we have FP perpendicular. And this is perpendicular to FP, of course. Okay, so this is 90 degree, this is 90 degree, this is theta. Okay, sorry, I might not have made sense now. Let me make sense. Okay, so what we're looking at is, say, this is FB, right? Oh, let me draw this. This is BC, sorry, not FB. This is BC. If this is BC, and if I turn an angle of theta, it becomes AC. Is that correct? Next, this is the perpendicular line. If I turn it by some angle, we don't know what angle is that. This is theta though. It is in line with FP, but we know that this is 90 degree and this is 90 degree. So for the relationship to be maintained, this has to be theta. Again, I repeat. So we have the line. I'm rotating this by an angle of theta. This line, I'm rotating this by an angle of theta. Only then this will be 90 and this will continue to be 90. Okay. So this is 90 and I'm telling this is also 90. Since this rotated by theta, this also has to be rotated by theta. Does this make sense? Think about it. Do the same thing. Just take two pencil. Keep it over here, one keep it over here. So for this two to be continue to be 90 degree, if I rotate this by say some 30 degree, this also has to be rotated by 30 degree. So that's the whole funda. So if this is theta, this has to be theta. Why? So we got to understand that this is theta, this is theta. So vertically opposite angle, this is theta. Okay, yes. Now when we resolve it, we have the following relationship. So we have FB sine theta and this is FB, this is cos. And this will be FB sine theta. Okay. Good. Now let's write that off. So we are looking at the system to be at equilibrium, right? As the system is in equilibrium along the horizontal direction. What we have is, let's have a look. FC is equal to FB sine theta. FC is equal to FB sine theta. Then along the vertical direction, what we have is FA. This will be FA FP cos theta, right? It's simple set of statements from the free body diagram. We're going to do one more thing from the figure, from the geometrical figure in specific. What we have here is we have a relationship between AB, BC and AC and theta using trigonometry that you guys know. Opposite by hypotenuse is your sine theta. Now taking up that relationship. So just a second. This is C, right? I'm going to write AC by AB is equal to sine theta. Do you guys agree? AC is this surface and AB is this surface. I'm extending it to 2-dimension. Trigonometry, I'm extending it to 2-dimension now. Opposite by hypotenuse is sine theta. So basically AC is equal to AB sine theta, right? And similarly what we have is AA will be equal to AB cos theta. So using all of this, we can prove one of the statements. So if I divide 1 and Okay. If I divide, then I'll get two relationships. Just a second, guys. I'm looking at FC, AB. Oh, yeah. Oh, no. We'll get it. So I'm going to divide 1 with, where is it? 3. So FC by AC, I'll get FC by AC. Let me write it here itself. FC by AC is equal to FB sine theta by AB sine theta. So what happens over here? Sorry about the handwriting. So FC by AC is nothing but PC. FB by AB is PB. You guys agree? So pressure is PC is equal to pressure PB. That is the force or the pressure along this surface is same as along this surface, and this surface is what we are proving actually. So when I divide 2 and 4, we'll get the other result. 2 getting divided by 4, what we have here is FA by AA is equal to FB cos theta by AB cos theta. So very simple derivation. So this and this will get cancelled. So we have PA is equal to PB. So therefore PA is equal to PB is equal to PC. And this goes back to the statements over here. The pressure in a fluid at rest is same at all points if we ignore gravity. Okay, so it leads to this. It's a very simple thing, right? Okay, so we just proved that mathematically. We just proved that the pressure in any given direction at a point is same. So let me just conclude this. So from this we can infer what? Pressure exerted is same in all direction. In all direction in a fluid at rest. Okay. So yeah, one by one, slowly we will understand quite a few more statements about Pascal's law. For now, you guys can just start with this.